We're exploring two particles that honestly couldn't seem more different. Yet they're both indispensable to how we understand the cosmos. Our mission here is to give you a shortcut, sort of, to understanding the cutting edge of fundamental physics. We'll do that by unpacking these two entities, the Higgs boson, the particle of mass, and the graviton, the much more elusive quantum of gravity. And we're drawing directly from a really fascinating comparative analysis called Higgs and Graviton, Scalar and Tensor Foundations of Reality. So when we talk about the universe, modern physics kind of stands on these two monumental pillars. First up, there's the Standard Model. This is our, remarkably successful quantum field theory. It describes all the fundamental matter, think quarks, leptons, that sort of thing, and their interactions, electromagnetism, the weak and strong nuclear forces, and it's been verified with just mind-boggling precision. It really works. Then on the other hand, we have general relativity. Einstein's theory, our most profound theory of gravity. It describes gravity not as a force exactly, but as the curvature of space-time itself. And like the Standard Model, it's also been verified with extraordinary accuracy.
It is quite remarkable, isn't it? You've got these two incredibly successful theories, each painting a near-perfect picture of its own domain.
Yeah.
Yet, and this is the big but, when you try to bring them together, the Standard Model and general relativity remain fundamentally compatible. The quest to unify them is, you could argue, it's the deepest challenge in theoretical physics today.
And right there, at the heart of this challenge, lie our two main characters for today, the Higgs boson and the graviton. The Higgs, that's the capstone of the Standard Model. It was famously confirmed, you remember, at CERN back in 2012. It's the quantum ripple, you could say, or an excitation of this unique space-filling field, the Higgs field, and that's what's responsible for giving fundamental particles mass. Its discovery wasn't just, big news. It was the final puzzle piece, the ultimate experimental proof for the Standard Model.
Yeah, and then in stark contrast, you have the graviton. This is the hypothetical quantum particle we expect to find if we apply quantum mechanics to general relativity. It would be the mediator of the gravitational force, sort of like how a photon mediates electromagnetism. But here's the kicker. It has never, ever been directly observed. And, maybe more importantly, every attempt to build a simple quantum field theory for gravity, something like the Standard Model, it's just completely failed. The calculations consistently lead to these uncontrollable infinities. It's a problem we call non-renormalizable.
Okay, hold on. So we have one confirmed particle, the Higgs, that perfectly completes our best theory of particles. And then we have this other hypothetical particle, the graviton, that actually breaks our best methods when we try to put it into the quantum world. That's a profound disconnect, isn't it? What does that tell us about the limits of, what we currently understand? The Higgs seems like the poster child for a successful, calculable theory.
And the graviton, conversely, is really the prime example of where that very paradigm breaks down.
Yeah.
The mere existence of these two particles and their just wildly differing theoretical tractability, it forces us to confront the boundaries, the edges of our current understanding of the universe. The Higgs represents the known, the calculable, the confirmed. The graviton, that's the unknown, the problematic. It's the frontier.
Let's really peel back the layers on the Higgs first then, because its story is fascinating. It's like this missing puzzle piece that just perfectly snaps into place. It solved a decades-long mystery right at the heart of how particles get their heft. You see, the electroweak theory, that's the theory combining electromagnetism and the weak nuclear force at high energies, it had this massive headache. For the theory to be consistent, mathematically sound, it required all its fundamental particles to be massless. But we know that's not true. We know the W and Z bosons and quarks and electrons, they definitely have mass. Some are quite heavy. So how did the Higgs solve this seemingly impossible conflict without just tearing the whole beautiful theory apart?
Right, it's all about something called gauge invariance. It's a deep symmetry principle. Think of it like this. Gauge invariance is the bedrock, the absolute foundation of these theories. It ensures they work consistently, no matter how you look at them, mathematically. Putting in mass terms explicitly, just writing them into the equations, would be like punching a huge hole in that bedrock. It breaks the symmetry. So the Higgs mechanism, developed by Brout-Englert-Higgs, found this incredibly clever workaround. It doesn't put mass in directly. Instead, it lets the universe's vacuum state itself do the heavy lifting through something called spontaneous symmetry breaking.
Whoa, okay, so instead of the fundamental laws being broken, the vacuum state, the sort of emptiness of space itself, is what breaks the symmetry. That's wild. Tell us more about this Higgs field.
Well, the theory posits this pervasive space-filling field, the Higgs field. It's everywhere. And this field has a unique potential energy function. People often visualize it as looking like a Mexican hat or maybe the bottom of a wine bottle. Now, crucially, its lowest energy state, the potential minimum, isn't at zero field value like you might intuitively expect for an empty void. No, it's at a non-zero value. The universe, as it cooled after the Big Bang, sort of rolled down into this minimum energy state, settling into one of these non-zero ground states. This gives the Higgs field a constant value everywhere in space, what we call its vacuum expectation value, or VEV. It's about 246 giga-electron volts, 246 GeV. And this choice, picking one specific ground state out of many possibilities, is what spontaneously breaks the original electroweak symmetry, leaving only the U1 symmetry of electromagnetism unbroken.
So it's like the entire universe collectively decided to roll down into one specific valley of this Mexican hat potential and just stayed there. That's quite a cosmic decision. And the Higgs boson particle, the thing they found at CERN, is a direct consequence of this field existing.
Exactly. The physical particles we observe, they're quantum excitations, like ripples, on their corresponding fields. In the Brout-Englert-Higgs mechanism, three aspects, or degrees of freedom, of the Higgs field are effectively eaten by the W and Z bosons. This is what gives them their longitudinal polarization components, basically. It allows them to behave like massive particles, and that's how they get their mass. The remaining degree of freedom, the one that's left over, that manifests as the Higgs boson itself. It's a specific type of excitation, a radial one, a fluctuation in the magnitude of the Higgs field around its VeV. It's a skin-zero particle, CP even, and its mass, which is around 125 GeV, depends on the specific parameters of that Higgs potential shape.
That's incredible, really. So the vacuum itself isn't truly empty in the classical sense. It's teeming with this energy field, this field that's responsible for everything having mass. That's fundamentally changing how you think about empty space. But if this field gives particles mass, how exactly do those interactions happen? How does a particle feel the field?
Well, it happens in slightly different ways. For the W and Z bosons, their interaction with the Higgs VeV mathematically just transforms directly into the mass terms in the equations, quite direct. And the photon, crucially, is associated with the symmetry that didn't get broken, electromagnetism's U1 symmetry. So it doesn't interact in this way, and it remains completely massless, just as we observe. Now, for the other fundamental particles, the matter particles like quarks and leptons, electrons, muons, terraces, they acquire mass through a different kind of interaction called Yukawa coupling. They interact with the Higgs field via these Yukawa couplings. And when the Higgs field gets its VeV, this interaction effectively gets converted into a standard mass term for those particles.
Ah, okay. So the strength of that Yukawa coupling is different for each particle, and that determines how heavy it ends up being.
Precisely. That's the key. This explains the huge hierarchy of masses we see in the standard model. The top quark, for instance, has a Yukawa coupling, very close to 1, which is quite strong in particle physics terms. And that makes it incredibly heavy, around a 173 GeV, while the electron, its Yukawa coupling is tiny, something like 10 ol, maybe even smaller, and so it's very, very light. And neutrinos, well, in the simplest version of the standard model, they lack a right-handed component, so they don't have this kind of Yukawa coupling. Within this basic framework, they remain massless, though we now know they do have a tiny mass, which hints at physics beyond the standard model. But that's another story.
Okay, so the Higgs is the confirmed architect of mass within the standard model framework. Now let's pivot hard to the graviton. It's such a contrast. It emerges not from particle interactions within spacetime, but from the quantization of spacetime itself. It's tied to the yet unwritten story of quantum gravity. We know general relativity is a classical field theory. Spacetime geometry is described by this thing called the metric tensor, GING, and Einstein's field equations, they're the rules that connect how spacetime curves to the distribution of mass and energy within it, represented by the stress energy tensor.
That's right. Now, to try and quantize it, to apply the rules of quantum mechanics, physicists often start with an approximation. They look at gravity as tiny fluctuations, small perturbations, little ripples, denoted him, happening on top of a flat space-time background. This process, called linearized gravity, simplifies Einstein's very complex equations into something that looks more like a standard wave equation. It's quite analogous, actually, to how Maxwell's equations for electromagnetism naturally lead you to predict the photon, the quantum of light.
And a graviton, then, is the elementary quantum particle associated with this perturbation field here. And crucially, it must be spin 2. That comes directly from the fact that gravity is described by a symmetric rank 2 tensor field, the metric tensor. That spin 2 nature is directly responsible for the weird polarizations we see, or rather detect, in gravitational waves, that characteristic plus and cross X stretching and squeezing of space. And just like the photon for the long-range electromagnetic force, gravity is also long-range, so its mediator, the graviton, must be massless. Now here's where, for me, it gets really interesting. Not only is the graviton tied intrinsically to space-time, but its very spin, that spin 2 nature, is supposedly what explains why gravity always pulls things together. It's always attractive. How does that work?
That's a really crucial point, yeah. You think about exchanging quantum particles to mediate forces. Exchange of a spin 1 particle, like the photon and electromagnetism, can lead to both attraction and repulsion. Think like charges repel, opposite charges attract. But the exchange of a spin 2 particle, provided its source, its charge, is always positive, like mass energy is always attractive. There's no repulsion possible in the same way. This is the quantum field theory explanation for gravity's universal attraction. It's baked into the spin 2 nature of the mediator. And what's the source for gravity? It's the stress-energy tensor. This tensor accounts for all forms of energy and momentum, mass, kinetic energy, pressure, everything. This universality, the fact that gravity couples to everything with energy, is absolutely core to gravity. It's related to the equivalence principle.
And there's always a but with the graviton, it seems. This very universality, this idea that gravity interacts with everything, including itself, since gravitons carry energy, is precisely what leads to its biggest theoretical headaches. Let's tackle this non-renormalizability problem head-on. You said the calculations lead to infinities. Why can't we just sweep them under the rug like we do in the standard model?
Right, so imagine you're doing calculations in quantum field theory. You have to account for quantum corrections, the effects of virtual particles popping in and out of existence, forming loops in your diagrams. For gravity, when you calculate these corrections involving virtual graviton loops, the answers you get are infinite, divergent. Now, in the standard model, which is a renormalizable theory, these infinities appear too, but they appear in a very structured, limited way. You can absorb all those infinities by cleverly redefining a finite number of parameters that were already in your theory, things like the fundamental particle masses and coupling strengths. You measure these values, plug them in, and all the infinities cancel out perfectly. It works beautifully. But for gravity, it fails spectacularly. Why? It boils down to the nature of Newton's gravitational constant. G is what physicists call dimensionful. It has units of inverse mass squared or energy squared. The coupling constants in the standard model are mostly dimensionless numbers.
Okay, dimensionful. What does that actually imply in this context? Why does having units mess things up so badly for quantum gravity calculations?
Well, having dimensions means the effective strength of gravity changes drastically with energy scale. Unlike, say, the fine structure constant in electromagnetism, which is dimensionless and changes only slowly, logarithmically, with energy. Because G has dimensions of inverse energy squared, it means that as you go to higher and higher energies, or probe smaller and smaller distances, gravity's quantum effects become stronger and stronger, much more rapidly than the other forces. This dimensionful nature causes new, more severe types of infinities to appear at every higher order of calculation in perturbation theory, those loop diagrams. To cancel these new infinities, you'd need to introduce an infinite number of new, arbitrary parameters into the theory at each step. A theory that needs an infinite number of parameters to make predictions is, well, it's useless. It has no predictive power. So this non-renormalizability is a profound signal. It tells us that trying to quantize general relativity using standard quantum field theory techniques just doesn't work at high energies. The linearized quantum gravity picture, with the graviton as a simple ripple, is likely just a low-energy approximation, an effective field theory.
So it strongly suggests we need a completely different framework, something more fundamental, like string theory, especially when we get close to the Planck scale, that incredibly high energy scale around 10 eldov. And it seems like the very universality of gravity is part of the problem. Gravitons carry energy, so they interact with themselves, creating these uncontrollable self-interaction loops at high energies.
That's exactly right. Gravity coupling to itself is intrinsically linked to the problem.
Okay, we've gone deep into the individual stories, but the real revelation, I think, comes when we really put the Higgs and the graviton side by side. Let's start with the most obvious difference, their spin. We touched on this, but what does it really mean for one to be spin 0 scalar and the other spin 2 tensor? How does that fundamentally shape what they are?
It's a huge difference. The Higgs being spin 0, a scalar particle, means it has no intrinsic directionality. It's like a single number at each point in space.
Its field's vacuum expectation value gives the vacuum a magnitude, this 246 GeV value, but it doesn't pick out a preferred direction in space, and that's absolutely crucial for preserving Lorentz invariance, the principle that the laws of physics look the same for all observers no matter how they're moving. The Higgs VeV doesn't create some weird cosmic ether wind. The graviton, being spin 2, a tensor particle, is fundamentally different. It does have intricate directional structure. It's described by multiple components that transform in a complex way under rotations. And we see this directly in gravitational waves. They don't just uniformly compress space, they stretch and squeeze it along specific axes. In that characteristic quadrupolar pattern, the plus and cross polarizations, that's a direct manifestation of its spin 2 nature.
And then there's their relationship with space-time itself. This feels like maybe the most profound distinction. You said the Higgs is a field that exists within space-time. The standard model sort of assumes space-time is this fixed background, like a stage. And the Higgs field populates that stage, interacting with the actors, other particles, and changing their properties, like giving them mass.
Precisely. The standard model is formulated on a pre-existing space-time manifold, usually assumed to be flat Minkowski space for calculations, or sometimes a curved background for cosmology. But the graviton is conceived as a quantum excitation of space-time itself. It's not just in space-time. In a very real sense, it is a ripple, a quantum wiggle of the dynamical geometry of the universe. So the failure to properly quantize gravity isn't just a technical problem with calculations. It's a fundamental failure to understand the quantum nature of the stage itself. How does space-time behave quantum mechanically? We don't fully know.
Wow. It's like one is a property of the stuff on the stage and the other is the stage at its most fundamental quantum level. That is genuinely mind-bending.
It really is. And what's fascinating, connected back to what we said earlier, is how these two particles, even though they're both bosons, force carriers or related to fields, spring from entirely different classes of symmetries. The Higgs emerges from the dynamics of an internal gauge symmetry, the SU2L-U1Y electroweak symmetry. This symmetry relates different particle fields to each other in an abstract mathematical space, almost like a hidden pattern within the equations themselves. The graviton, however, is expected to arise from quantizing a theory, general relativity, whose fundamental symmetry is an external space-time symmetry. It's called diffeomorphism invariance, or general covariance.
Diffeomorphism invariance. Okay, break that down for us. For our listeners, what does that really imply about the laws of physics? What does that symmetry mean?
It means, essentially, that the laws of physics don't depend on the particular coordinate system you choose to describe events in spacetime. Whether you use latitude and longitude on Earth, or Cartesian XYZ coordinates, or some completely arbitrary distorted grid, you draw the underlying physical reality, and the equations describing it remain the same. Physics is independent of your map-making choices. The graviton is thought to be the quantum manifestation associated with this fundamental principle, this independence of physics from our arbitrary descriptions of space-time location.
Okay, let's shift gears to their interactions and couplings. Here we see this dramatic disparity, this enormous gap that reveals one of the deepest, most persistent mysteries in fundamental physics. For the Higgs, you mentioned its couplings to matter particles. The fermions are these dimensionless Yukawa constants. And crucially, these are free parameters in the standard model. The theory doesn't predict their values. We have to measure them. And they span this huge range. The top quark's coupling is near 1, while the electron's is tiny, around 3 by 10 a year or so. This directly explains the vast mass differences we see, the hierarchy of fermionesses.
That's correct. The Higgs couplings are specific to each particle type. The graviton's coupling, on the other hand, is completely universal. It couples to everything that has energy or momentum, as we discussed. And its strength isn't a free parameter in the same way. It's fundamentally fixed by a single constant of nature, the Planck mass, MPL. The Planck mass is enormous, about 1.22 by 10 GeV/CL. That's the characteristic energy scale of quantum gravity. Now, if you calculate the effective dimensionless coupling strength of gravity at energies we typically probe in particle colliders, say around 1 TeV, or GeV, it's incredibly tiny. It's something like 1 TeV MPO, which is on the order of 10 Laker. This just highlights mathematically how extremely weak gravity is compared to the other fundamental forces at everyday energies.
And this immense difference in scales, the electroweak scale set by the Higgs VeV around 246 GeV, and the Planck scale of gravity at 10 erg leads us straight into the abyss known as the hierarchy problem. Why? Why is the Higgs mass around 125 GeV, which is tied to the electroweak scale, so incredibly ridiculously low and stable compared to the fundamental scale of gravity, the Planck scale? There's this gap of 17 orders of magnitude. You mentioned quantum corrections earlier. Expert, explain how these corrections threaten to blow up the Higgs mass and why it leads to this fine-tuning problem. You compared it to canceling out the Earth-Sun distance down to a millimeter. That sounds impossible.
It sounds impossible, and that's why physicists find it so unnatural. Here's the issue. For a scalar particle, like the Higgs, spin-zero particles are particularly sensitive to this. Quantum corrections involving loops of virtual particles tend to be very large. Specifically, the dominant corrections contribute an amount proportional to the square of the highest energy scale up to which the theory is valid, often called the cutoff scale. Now, if we assume the standard model, perhaps with gravity included somehow, is the correct description of physics all the way up to the Planck scale, then that cutoff would be around the Planck mass, 10 to 5 GeV. So these quantum corrections to the Higgs mass squared should be enormous, something like 10 to the huge. But we measure the Higgs mass to be about 125 eGeV. For the physical Higgs mass to be so small, the bare Higgs mass parameter in the original theory must be almost exactly equal and opposite to these gigantic quantum corrections. They would have to cancel each other out with a precision of about 1 part in 10 UNs. That's like measuring the distance to the sun and needing to know it accurately to within the width of a human hair to get the final answer right. This extraordinary, seemingly coincidental cancellation is what we call the fine-tuning problem. It feels deeply unnatural for a fundamental theory to require such an absurdly precise adjustment of its parameters.
So it's not that the math doesn't work, it's that it requires this unbelievable coincidence, this balancing act that seems too perfect to be accidental. And this numerical chasm, this hierarchy problem, it's a direct consequence of having both a light scalar particle, the Higgs, and gravity, with its high Planck scale, coexisting in the same universe. It's like the universe is whispering, or maybe shouting, that our current picture is incomplete. It's a powerful signpost, isn't it? Hinting at hidden layers of reality. Maybe new symmetries like supersymmetry or perhaps extra spatial dimensions.
Exactly. The hierarchy problem is arguably the most significant numerical clue we have, pointing towards the existence of new physics beyond the standard model, likely appearing somewhere around the TV energy scale, not too far above the Higgs mass itself. Physics that would naturally explain why the Higgs mass is light without requiring this insane fine-tuning.
Okay, let's turn to the experimental frontiers now. How we actually look for or study these particles. And here, you'll really see a stark contrast in their status. The Higgs boson, as we said, had its landmark discovery in 2012 at CERN's Large Hadron Collider, the LHC, by the ATLAs and CMS collaborations. A huge moment for physics. How is it actually produced in those collisions?
It's produced in several ways in the proton collisions at the LHC. The dominant process is called gluon fusion, GGF, where two gluons from the colliding protons interact, often via virtual top quark loop, to create a Higgs. But there are other important production modes too. Vector boson fusion, VBF, where quarks radiate W or Z bosons, which then fuse to make a Higgs. There's also associated production, VH, where a Higgs is produced alongside a W or Z boson. And even TTH production, where a Higgs is produced together with a top quark and an anti-top quark. This last one is particularly interesting because it directly probes the Higgs coupling to the top quark, that strong Yukawa coupling we mentioned.
But once it's produced, it decays almost instantly, right? So how do the experiments actually see it?
That's right. The Higgs is very short-lived. It decays in many different ways, and we detect it by looking for its decay products. Some key decay channels include H decaying into 2 photons. This is a very clean channel, giving a sharp peak in the data above the background. H decaying into 2 sozons, which then each decay into pairs of leptons, electrons, or muons, so H is at 4. This is often called the golden channel because it provides a very clear, unambiguous signature. There's also H decaying into 2 W bosons, HIWO2, which results in 2 leptons and missing energy from the neutrinos. And, crucially for confirming its role in mass generation, decays into pairs of heavier fermions, like HL bottom quarks and 8+ tau leptons. Observing these confirms the Higgs couples to fermions and proportionally to their mass as predicted. Since 2012, the experimental focus has really shifted from discovery to precision measurement, meticulously measuring all these production rates and decay branching ratios. And the remarkable thing is, so far, all the measurements are stunningly consistent with the predictions of the standard model Higgs boson. They confirm its spin zero, CP even nature, and its predicted couplings to an impressive degree.
It really is astounding. We have this incredibly complete, consistent experimental picture of the Higgs. Every new measurement seems to just slot perfectly into the standard model framework. But then we turn to the Graviton, and it's a completely different universe experimentally. You said direct detection of a single individual graviton is considered physically impossible. Why is it so incredibly elusive?
It comes down to that extremely weak coupling strength we talked about, suppressed by the Planck mass squared. The probability of any given particle interacting via gravity by emitting or absorbing a single graviton is just infinitesimally small. The cross-section, as physicists call it, is practically zero for any conceivable detector. Trying to detect a single graviton emitted from, say, a particle decay would be far, far harder than finding a specific grain of sand on all the beaches of the world combined. It's not feasible. Therefore, any evidence we have for the graviton is necessarily indirect. It's based on observing classical gravitational phenomena, which, theoretically, must be composed of a vast number, an enormous coherent state of these individual gravitons. We actually got stunning Nobel Prize-winning indirect confirmation back in the 1970s from observing binary pulsar systems, like the Hulse-Taylor pulsar. Astronomers measured the rate at which the two neutron stars were spiraling in towards each other. The rate of orbital decay perfectly matched the predictions of general relativity for energy loss due to the emission of gravitational waves, the classical manifestation of gravitons. The agreement was better than 0.2%.
Right, that was huge. Indirect evidence, but incredibly precise. And then, of course, the modern era began in 2015 with the first direct detection of gravitational waves by LIGO and Virgo from merging black holes. This was monumental because it confirmed the existence of these propagating ripples in spacetime itself, the classical wave whose quantum excitation must be the graviton if our understanding of quantum field theory is applicable. So we're left with this fascinating paradox, aren't we? For gravity, we have definitive proof of the classical wave phenomena, gravitational waves, but we can only infer the existence of the quantum particle, the graviton, which is the complete reverse of light, where the particle nature, the photon, was experimentally established first through things like the photoelectric effect, well before the full classical wave theory of electromagnetism was completely understood.
That's a perfect way to put it. This distinct experimental status for the Higgs and the graviton really highlights the different ways we have to probe reality. Sometimes we can isolate and study individual quantum particles directly in accelerators. Other times, we have to observe the collective large-scale effects of those quanta playing out across cosmic distances, like ripples in the fabric of spacetime itself.
Okay, so given these immense theoretical challenges with the graviton, the non-renormalizability, its role in the hierarchy problem, these issues are really the primary drivers for exploring new physics, for going beyond the standard model, or BSM, as physicists say. These BSM theories are essentially attempts to find a more fundamental framework that can naturally unify the Higgs and the graviton, resolving these problems. Expert, what are some of the leading ideas out there? String theory always comes up.
String theory is certainly a leading candidate, perhaps the most developed framework we have for a potentially consistent theory of quantum gravity. The fundamental idea is to replace point particles with tiny one-dimensional vibrating strings. The different modes of vibration of these strings correspond to the different fundamental particles we see. Now, a key prediction, something that comes out automatically from the mathematics of string theory, is that one particular vibrational mode of a closed string, a loop, has precisely the properties required of a massless spin-2 particle. In other words, string theory doesn't just accommodate gravity. It requires the existence of the graviton. It predicts it. Furthermore, the fact that strings are not points, but have a tiny extension, is thought to smooth out the problematic point-like interactions that lead to the infinities in standard quantum field theory, potentially resolving the non-renormalizability problem. And other features, like Higgs-like scalar fields and the gauge symmetries of the standard model, can also potentially be realized within different string theory constructions or compactifications.
That sounds incredibly elegant, almost too good to be true sometimes. What about other approaches? I know people talk about extra dimensions as a way to tackle the hierarchy problem.
Yes, that's another major avenue of BSM research. The idea is that perhaps there are more spatial dimensions than the three we directly perceive. In specific models, like the Randall-Sundrum models, our universe, with its three spatial dimensions plus time, so 4D spacetime, is pictured as a brane, like a membrane embedded within a higher dimensional space, often called the bulk. The idea is that the standard model particles and forces, electromagnetism, weak, strong, are confined to live on this brane, but gravity, mediated by the graviton, can propagate through the entire higher dimensional bulk space.
Okay, interesting. But how does that help with the huge energy gap, the hierarchy problem? Does it make gravity stronger somewhere else?
It can, effectively. In some models, particularly those with a warped geometry in the extra dimension, the fundamental scale of gravity, the true Planck scale, could actually be much lower than the 10^10 we perceive. It might even be down near the TV scale, close to the electroweak scale set by the Higgs. The reason gravity appears so weak to us on our brane is because its strength is diluted, exponentially suppressed, by leaking out into the large volume of the extra dimensions, or due to the warping of the geometry. So the incredible weakness of gravity in our 4D experience becomes a kind of geometric illusion. If this is true, the hierarchy problem essentially vanishes. The fundamental scales wouldn't be that different after all. And these extra-dimensional theories often make quite specific testable predictions. For example, they predict the existence of massive Kaluza-Klein excitations, essentially copies of the graviton and other particles, which correspond to vibrations or momentum in the extra dimensions. These KK gravitons could potentially be heavy enough to be produced and detected at the LHC, although searches so far haven't found them.
Fascinating stuff. Extra dimensions, vibrating strings. It really pushes the boundaries. And finally, there's also some research, maybe more speculative, that tries to connect the Higgs field directly to the very early universe, specifically to cosmic inflation.
That's right. There's a class of models called Higgs inflation. We know the very early universe likely underwent a period of incredibly rapid exponential expansion called cosmic inflation. This is thought to have been driven by the potential energy of some scalar field, dubbed the inflaton. Higgs inflation models propose the radical idea that the standard model Higgs field itself could have played the role of the inflaton. Now, the standard Higgs potential doesn't quite work for inflation on its own, so these models typically require introducing a new non-minimal coupling term that directly links the Higgs field to the curvature of spacetime, represented by the Ricci scalar, bar something like HA. This extra coupling term can effectively flatten the Higgs potential at very high energy densities, allowing it to slowly roll and drive inflation in the early universe. If true, this would represent a really profound direct connection between the architect of particle mass, the Higgs, and the large-scale evolution of spacetime, gravity and inflation, unifying aspects of Higgs physics and cosmology in a very direct way.
So if we try to connect all these threads, these theoretical proposals, string theory, extra dimensions, Higgs inflation, they all seem to be born from tackling the challenges posed by the Higgs and graviton coexisting. And they all point towards a deeper reality, don't they? A reality where the Higgs and the graviton might not be such independent entities after all, but maybe different facets, different manifestations of a single unified underlying structure. It suggests the solution to these deep puzzles might really involve fundamentally rethinking reality, seeing it as something much more complex, maybe higher dimensional, maybe stringy, than our current standard model plus general relativity picture allows.
Okay, let's try to quickly recap the core comparison then. We have the Higgs boson, spin-zero scalar, the architect of mass, arising from an internal gauge symmetry. It's renormalizable, experimentally discovered, and fundamentally exists within spacetime. Check.
And the graviton. Hypothetical spin-2 tensor, the mediator of gravity itself, arising from a fundamental spacetime symmetry. It's non-renormalizable within standard methods, remains hypothetical, and is conceived as a quantum excitation of spacetime. Check. But despite these stark fundamental differences, we need both, right? Both are indispensable bosons that seem demanded by our most successful theories to explain the cosmos as we see it. The Higgs is crucial for mass. Without it giving mass to particles like electrons and quarks via the BEH mechanism, you don't get stable atoms, you don't get chemistry, stars, planets, you don't get us. And the graviton, or at least the gravity it mediates, is essential for sculpting the entire large-scale structure of the universe holding galaxies together, driving cosmic expansion.
Absolutely. And the chasm that separates them, a huge numerical gap expressed as the hierarchy problem, and the deep theoretical incompatibility highlighted by non-renormalizability, that chasm isn't really a failure of physics. It's probably the clearest, most glaring signpost we have, pointing the way forward. It tells us emphatically that the standard model and general relativity, despite their incredible successes, cannot be the final word. They're incomplete pieces of a larger puzzle.
So the ultimate quest, the search for a theory of everything, really has to bridge this divide. It needs to be a theory that naturally incorporates both a light scalar particle like the Higgs and a massless tensor particle like the graviton, and crucially, explains why there's this vast 17 orders of magnitude energy gap between their associated scales.
Precisely. And the search for clues continues relentlessly on dual fronts. On one side, you have the high-energy frontier with particle colliders like the LHC, making ever more precise measurements of the Higgs boson's properties, searching for tiny deviations that might hint at new physics, looking for direct production of BSM particles. And on the other side, you have the cosmic frontier observatories studying gravitational waves from cataclysmic events, looking at the cosmic microwave background radiation for subtle imprints of quantum gravity or inflation from the very beginning of time.
It's an exciting time. So let's leave our listeners with a final thought. Imagine a future, maybe decades or centuries from now, where these two seemingly disparate entities, the Higgs and the graviton, are finally understood. Understood not as separate things, but as two essential, maybe even inseparable facets of a single, coherent, unified description of reality. What entirely new questions might that deeper understanding open up about the very nature of existence itself? Something to ponder.